Welcome to BNDF Institute. Today, we are sharing an exceptional lecture from Harvard University CS50 AI course taught by Professor David Malan. In this session, we will explore the fundamentals of artificial intelligence, including machine learning, large language model, generative AI, and the core ideas behind modern AI systems that power tools like ChatGPT, Gemini, and other intelligence applications.
All right, this is CS50, and this is our lecture on artificial intelligence, or AI, particularly for all of those family members who are here in the audience with us for the first time. In fact, for those students among us, maybe a round of applause for all of the family members who have come here today to join you. Nice. So nice to see everyone. And as CS50 students already know, it's sort of a thing in programming circles to have a rubber duck on your desk. Indeed, a few weeks back, we gave one to all CS50 students. And the motivation is to have something to talk to in the presence of a bug or mistake in your code or confusion you're having when it comes to solving some problem. And the idea is that in the absence of having a friend, family member, TA of whom you can ask questions, is to literally verbalize your confusion, your question, to this inanimate object on your desk. And in that process of verbalizing your own confusion and explaining yourself, quite often does that proverbial light bulb go off over your head, and voila, problem is solved. Now, as CS50 students also know, we sort of virtualized that rubber duck over the past few years, and most recently in a form of this guy here. So in students' programming environment within CS50, a tool called Visual Studio Code at a URL of cs50.dev, they have a virtual rubber duck available to them at all times. And early on, in the very first version of this rubber duck, it was a chat window that looked like this. And if students had a question, they could simply type into the chat window something like, "I'm hoping you can help me solve a problem." And for multiple years, all the CS50 duck did was respond with 1, 2, or 3 quacks. We have anecdotal evidence to suggest that that alone was enough for answering students' questions, because it was in that process of actually typing out their confusion that you realize, oh, I'm doing something silly, and you figure it out on your own. But of course, now that we live in an age of ChatGPT and Claude and Gemini and all of these other AI-based tools, came as no surprise, perhaps, when in 2023, this same duck started responding to students in English. And that now is the tool that they have available, which is, in effect, meant to be a less helpful version of ChatGPT, one that doesn't just spoil answers outright, but tries to guide them to solutions akin to any good teacher or tutor. And so today's lecture is indeed on just that, and the underlying building blocks that make possible that there rubber duck and all of the AI with which we're all increasingly familiar, namely generative artificial intelligence, using this technology known as AI to generate something, whether that's images or sounds or video or text. And in fact, what we thought we'd do to get everyone involved early on is, if you have a phone by your side, if you'd like to go ahead and scan this QR code here. And that's going to lead you to a polling station where you can buzz in with some answers. CS50's preceptor Kelly is going to kindly join me here on stage to help run the keyboard. And what we're about to do is play a little game and see just how good we humans are right now at distinguishing AI from reality. And so we'll borrow some data from the New York Times, which a couple years back actually published some examples of AI and not AI. And we'll see just how good this technology has gotten. So here we have 2 photographs on the screen. In a moment, you'll be asked on your phone, if you were successful in scanning that code, which one of these is AI, left or right? So hopefully on your phone here, if you want to go ahead and swipe to the next screen, we'll activate the poll here. In a moment, you should see on your phone a prompt inviting you to select left or right. And feel free to raise your hand if you're not seeing that. But it looks like the responses are coming in. And at the risk of spoiling, it looks like 70% plus of you think it is the answer on the right. And if, Kelly, maybe we could swipe back to the 2 photographs. In this particular case, yes, it was, in fact, the one on the right. Maybe it looked a little too good, or maybe a little too unreal. Maybe, let's see, maybe a couple of other examples. So same QR code, no need to rescan. Let's go ahead and pull up these 2 examples now. 2 photographs, same question. Which of these is AI, left or right? Left or right? All right, I want to take a look at the chart, see what the responses are coming in. A little closer in this case, but a majority of you think the answer is in fact left here, though 5% of you are truthfully admitting that you're unsure. But Kelly, if you want to swipe back to the photos, the answer this time was in fact a trick question. They were both in fact AI, which perhaps speaks to just how good this technology is already getting. Neither of these faces exists in the real world. It was synthesized based on lots of training data. So 2 photographs that look like humans, but do not in fact exist. How about one more, this time focusing on text, which will be the focus, of course, underlying our duck. Did a 4th grader write this or the new chatbot? Here are 2 final examples. Same code as before, so no need to rescan. And here are the texts. SA1. I like to bring a yummy sandwich and a cold juice box for lunch, and sometimes I'll even pack a tasty piece of fruit or a bag of crunchy chips. As we eat, we chat and laugh and catch up on each other's day. ... SA2, my mother packs me a sandwich, a drink, fruit, and a treat. When I get into a lunchroom, I find an empty table and sit there and eat my lunch. My friends come and sit down with me. ... The question now, lastly, is which of these is AI? 1 or 2? SA1 or 2? The bars here are duking themselves out. It looks like a majority of you say SA1. Let's go back to the text. And one of you who says SA1, why? If you want to raise a quick hand. Why SA1? Yeah. OK, and so SA2 looks more like you would, right? And can I ask what grade you are in? Oh, 5th grader. So is this a new 5th grader or not? The answer here, in fact, is that SA1 is the AI because, indeed, SA2 is more akin to what a 4th or, if I may, a 5th grader would write. And I dare say there are maybe some telltale signs. I'm not sure a typical 4th grader or 5th grader would catch up on each other's day in the vernacular that we see in SA1. But suffice it to say, this game is not something we can play in the years to come because it's just going to get too hard to discern something that's AI generated or not. And so among our goals for today is really to give you a better sense of not just how technologies like this duck and these games that we've played here with images and text work, but really what are the underlying principles of artificial intelligence that frankly have been with us and have been developing for decades and have really now come to a head in recent years thanks to advances in research, thanks to all the more cloud computing, thanks to all the more memory and disk space and information, sheer volume thereof that we have at our disposal that can be used to train all of these here technologies. So that there duck is built on a fairly complicated architecture that looks a little something like this, where here's a student using one of CS50's tools. Here's a website with which CS50 students are familiar called cs50.ai, where we, the staff, wrote a bunch of code that actually talks to what are called APIs, application programming interfaces, third-party services by companies like Microsoft and OpenAI that really have been doing the hard work of developing these models, as well as some local some local sauce that we, CS50, add into the mix to make it specific, the duck's answers to CS50 itself. But what we've essentially been doing is something with which you might be familiar, in part, prompt engineering, which has started popping up, for better or for worse, on LinkedIn profiles everywhere. And prompt engineering, really, it's not so much a form of engineering as it is a form of asking good questions and being detailed in your question, giving context to the underlying AI so that the answer with high probability is what you want back. And so there's 2 terms in this world of prompt engineering that are worth knowing about. So CS50 has leveraged both of these to implement that duck. We, for instance, wrote what's called a system prompt, which are instructions written by us humans, often in English, that sort of nudge the underlying AI technology to have a certain personality or a specific domain of expertise. For instance, we, CS50, have written a system prompt essentially that looks like this. In reality, it's like a lot of lines long nowadays, but the essence of it is this. You are a friendly and supportive teaching assistant for CS50. You are also a rubber duck. And that is sufficient to turn an AI into a rubber duck, it turns out. Answer student questions only about CS50 in the field of computer science. Do not answer questions about unrelated topics. Do not provide full answers to problem sets, as this would violate academic honesty. Answer this question, : And after that preamble, if you will, aka system prompt, we effectively copy-paste whatever question a student has typed in, otherwise known as a user prompt. And that is why the duck behaves like a duck in our case, and not a cat or a dog or a PhD, but rather something that's been attenuated to the particular goals we have pedagogically in the course. And in fact, those of you who are CS50 students might recall from quite some weeks ago in week 0, when we first introduced the course to the class, we had code that we whipped up that day that ultimately looked a little something like this. And I'll walk through it briefly line by line. But now, on the heels of having studied some Python in CS50, this here code that I whipped up in the first lecture might make now a bit more sense. In that first lecture, we imported OpenAI's own library, code that a third-party company wrote to make it possible for us to implement code on top of theirs. We created a variable called client in week 0, and this gave us access to the OpenAI client, that is software that they wrote for us. We then defined in week 0 a user prompt, which came from the user using the input function with which CS50 students are now familiar. And then we defined this system prompt that day where I said, limit your answer to 1 sentence, pretend you're a ... cat, I think was the persona of the day. And then we used some bit more arcane code here, but in essence, we created a variable called response, which was meant to represent the response from OpenAI's server. We used client.responses.create, which is a function or method that OpenAI gives us that allows us to pass in 3 arguments. The input from the user, that is the user prompt, the instructions from us, that is the system prompt, and then the specific model or version of AI that we wanted to use. And the last thing we did that day was print out response.output_text. And that's how we were able to answer questions like, what is CS50 or the like. So we've seen all of that before, but we didn't talk about that week exactly how it was working or what more we could actually do with it. And so in fact, what I thought we'd do today is peel back a layer that we've not allowed into the course up until now. And indeed, you still cannot use this feature until the very end of the class in CS50 when you get to your final projects, at which point you are welcome and encouraged to use VS Code in this particular way. So here again is VS Code. For those unfamiliar, this is the programming environment we use here with students. And let me open up some code that was assigned to students a couple of weeks back, namely a spell checker that they had to implement in C. So I came in advance with a folder called Speller. And inside of this folder, I had code that day, and all students had that week, called dictionary.c. And in this file, which will not look familiar to many of you if you've not taken week 0 through 7 up until now, we did have some placeholders for students. So long story short, students had to answer a few questions, that is, write code to do this to do, this to do, this to do, and one more. There were 4 functions or blanks that students needed to fill in with code. And I dare say it took most students 5 hours, 10 hours, 15 hours, something in that very broad range. Let me show you now how using AI, you, soon the aspiring programmers, can start to write code all the more quickly, not by just choosing a different language, but by using these AI-based technologies beyond the duck itself. So what I've done here on the right-hand side of VS Code is enabled a feature that CS50 disables for all students from the start of the course called Copilot. This is very similar in spirit to products from Google and Anthropic and other companies as well. But this is the one that comes from Microsoft and in turn GitHub here. And it too gives us me sort of a chat window here. And this is just one of its features. For instance, if I wanted to implement, to get started, the check function, I could just ask it to do that. Implement the check function, and how about using a hash table in C? I'm going to go ahead and click Enter. Now it's going to work. It's using as reference, that is context, the very file that I've opened, which is dictionary.c here. Copilot in general, as well as a lot of AI tools, are familiar with CS50 itself because it's been freely available as open courseware for years. What you see here doing is essentially thinking, though that's a bit of an overstatement. It's not really thinking. It's trying to find patterns in what the problem is I want to solve among all of its training data that it's seen before and come up with a pretty good answer. So for today's purposes, I'm going to wave my hand at the ChatGPT-like explanation of what to do that was appeared at right. But what's juiciest to look at here is on the left, if I now scroll down, is highlighted in green is all of the suggested code for implementing this here check function. Now, it might not be the way you implemented it yourself, but I do dare say this has hints of exactly what you probably did when it came to implementing a hash table. And in fact, I can go ahead and keep all of this code if I like how it looks. Let's assume that's all correct there. It might be the case that I want to now implement the load function. So how about now implement load function? Enter. As simple as that. And what data is being used? Well, a few different things. It says one reference, so it's indeed using this one file. But there's also what are called comments in the code, with which all students are now familiar, these / commands in gray that are giving English hints as to what this function is supposed to do. There's implicit information as to what the inputs to these functions, otherwise known as arguments, are meant to be, what the outputs are meant to be. So the underlying AI, called Copilot here, kind of has a decent number of hints. And much like a good TA or a good software engineer, that's enough context to figure out how to fill in those blanks. And so here too, if I scroll down now, we'll see in green some suggested code via which it could solve that same problem as well, the load function. And I dare say I've been talking for far fewer minutes than CS50 students spent actually coding the solution from scratch to this here problem. So I'll go ahead and click keep. I'll assume that it's correct, but that's actually quite a big assumption. And those of you wondering, like, why have we been learning off all this if I could just ask in English it to do my homework for me? I mean, there's a lot to be said for the muscle memory that hopefully you feel you've been developing over the past several weeks. The reality is if you don't have an eye for what you're looking at, there's no way you're going to be able to troubleshoot an issue in here, explain it to someone else, make marginal changes or the like. And yet, what's incredibly exciting, even to someone like me, all of the staff, friends of mine in the industry, is that this kind of functionality in AI amplifies your capabilities as a programmer sort of overnight. Once you have that vocabulary, that muscle memory for doing it yourself, the AI can just take it from there and get rid of all of the tedium, allow you to focus at the whiteboard with the other humans on sort of the overarching problems that you want to solve, and leave it to this AI to actually solve problems for you. A fun exercise, too, might be to go back at term's end and try solving any number of the course's assignments. For instance, let me go ahead and do this. In my terminal window here, I'm going to go back to my main directory. I'm going to create an empty file called mario.c that has nothing in it. And I'm going to go ahead in my chat window here and say, please implement a program in C that prints a left-aligned pyramid of bricks using hash symbols for bricks, and use the CS50 library to ask the user for a non-negative height as an integer, period. I dare say that's essentially the English description of what was, for CS50 this year, problem set 1, to implement a program called mario.c. This, too, is sort of doing its thing. It's using one reference. It's working. It knows as a hint that this file is called mario.c, and it's seen a lot of those in its training data over time. There's an English explanation of what I should do, and those CS50 students in the room probably recognize the sort of basic structure here of using a do-while loop to prompt the user for a height, using the CS50 library, which has been included, print a left-aligned pyramid using some kind of loop, and boom, we are done. And these are fairly bite-sized problems, as you'll see as you get to term's end with your final project, which is a fairly open-ended opportunity to apply your newfound knowledge and savvy with programming itself to a problem of interest. It will allow you to implement far grander projects, far greater projects than has been possible to date, certainly in just the few weeks we have to do it, because of this amplification of your own abilities. So with that promise, let's talk about how in the heck any of this is actually working. I clearly just generated a whole lot of stuff, and that's how we began the story, with the generation of those images and those 2 essays by kids. But what is generative artificial intelligence, or really, what is AI itself? And these are some of the underlying building blocks that aren't going anywhere anytime soon, and indeed have led us as a progression to the capabilities you just saw. So spam, we sort of take for granted now that in our Gmail inboxes or Outlook inboxes, most of the spam just ends up in a folder. Well, there's not some human at Microsoft or Google sort of manually labeling the messages as they come in, deciding spam or not spam. They're figuring out using code, and nowadays using AI, that looks like spam, and therefore I'm going to put it in the spam folder, which is probably correct 99% of the time, but indeed there's potentially a failure rate. Other applications might include handwriting recognition. Certainly Microsoft and Google doesn't know the handwriting style of all of us here in this room, but it's been trained on enough other humans' handwriting styles that odds are your handwriting and mine looks similar to someone else's. And so with very high probability, they could recognize something like hello world here as indeed that same digital text. All of us are into streaming services nowadays, Netflix and the like. Well, they're getting pretty darn good at knowing if I watched X, I might also like Y. Why? Well, because of other things I've watched before and maybe upvoted and downvoted. Maybe because of other things people have watched who like similar movies or TV shows to me. So that, too, is AI. There's no if-else construct for every movie or TV show in their database. It's sort of figuring out much more organically, dynamically, what you and I might like. And then all of these voice assistants today, Siri, Alexa, Google Assistant, and the like, those, too, don't recognize your voice or necessarily know what questions you're going to ask it. There's no massive if-else if that has all possible questions in the world just waiting for you or me to ask it. That, too, of course, is dynamically generated. But that's getting a bit ahead of ourselves. Let's rewind in time, and some of the parents in the audience might remember this here game, among the first arcade games in the world, namely Pong. And so this was a black and white game whereby there's two players, a paddle on the left, a paddle on the right, and then using some kind of joystick or trackball, they can move their paddles up and down. And the goal is to bounce the ball back and forth and ideally catch it every time. Otherwise, you lose a point. This is just an animated GIF, so there's nothing really dramatic to watch. It's going to stay at 15 against 12, just looping again and again. Nothing interesting is going to happen, but this is a nice example of a game that lends itself to solving it with code. And indeed, it's been in our vernacular for years to play against not just the computer, but the CPU, the central processing unit, or really the AI. And yet AI does not need to be nearly as sophisticated as the tools we now see. For instance, here's a successor to Pong known as Breakout. Similar in spirit, but there's just one paddle and one ball. And the goal is to bounce the ball off of these colorful bricks, and you get more and more points depending on how high up you can get the ball. All of us as humans, even if you've never played this old school game, probably have an instinct as to where we should move the paddle. If the ball just left it going this way, which direction should I move the paddle? I mean, probably to the left. And indeed, that'll catch it on the way down. So you and I just made a decision that's fairly instinctive, but it's been ingrained in us. But we could sort of take all the fun out of the game and start to quantify it or describe it a little more algorithmically, step by step. In fact, decision trees are a concept from economics, strategic thinking, computer science as well. That's one way of solving this problem in such a way that you will always play this game well if you just follow this algorithm. So for instance, how might we implement code or decision-making process for something like Breakout? Well, you ask yourself first, is the ball to the left of the paddle? If so, you know where we're going. Then go ahead and move the paddle left. But what if the answer were no, in fact? Well, you don't just blindly move the paddle to the right, probably. What should you then ask? Are you right below the ball? If the ball's coming right at you, you don't want to just naively go to the right and then risk missing it. So there's another question to ask. Is the ball to the right of the paddle? And that's a yes/no question. If yes, well then, OK, move it to the right. But if not, you should probably stay exactly where you are and don't move the paddle. All right, so that's fairly deterministic, if you will. And we can map it to code using pseudocode in, say, a class like CS50. We can say in a loop, well, while the game is ongoing, if the ball's to the left of the paddle, then move the paddle left. Else, if the ball's to the right of the paddle, sorry for the typo there, move the paddle right. Else, just don't move the paddle. And so these decision trees, as we drew it, have a perfect mapping to code, or really pseudocode in this particular case, which is to say that's how people who implemented the Breakout game or the Pong game who implemented a computer player surely coded it up. It was as straightforward as that. But how about something like tic-tac-toe, which some of you might have played on the way in for just a moment on the scraps of paper that you might have had. Here we have a tic-tac-toe board with two O's and two X's. For those unfamiliar, this game, tic-tac-toe, otherwise known as knights and crosses, is a matter of going back and forth, X's and O's, between two people. And the goal is to get 3 O's in a row or 3 X's in a row, either vertically, horizontally, or diagonally. So this is a game here in mid-progress. Well, let's consider how you could solve the game of tic-tac-toe like a computer, like an AI might. Well, you could ask yourself, can I get 3 in a row on this turn? Well, if yes, well, play in the square to get 3 in a row. It's as straightforward as that. If you can't, though, what should you ask? Well, can my opponent get 3 in a row on their next turn? Because if so, you should probably at least block their move next, so at least you don't lose now. But this game, tic-tac-toe, is relatively simple as it is, gets a little harder to play when it's not obvious where you should go. Now, all of us as humans, if you grew up playing this game, probably had heuristics you used, like you really like the middle, or you like the top corner, or something like that. So we probably can make our next move quickly, but is it optimal? And I dare say if back in childhood or more recently you've ever lost a game of tic-tac-toe, like you're just bad at tic-tac-toe, because logically there's no reason you should ever lose a game of tic-tac-toe if you're playing optimally. At worst, you should force a tie, but at best, you should win the game. So think of that the next time you play tic-tac-toe and lose, like you're doing something wrong, but in your defense, it's because the question mark is sort of non-obvious. Like, how do I answer it when the answer is not right in front of me to move for the win or move for the block? Well, one algorithm you could have been using all of these years is called minimax. And as the name suggests, it's all about minimizing something and or maximizing something else. So here too, let's take a bit of fun out of the game and turn it into some math, but relatively simple math. So here we have 3 representative tic-tac-toe boards. O has 1 here, X has 1 here, and the middle is a tie. Doesn't matter how we score these boards, but we need a consistent system. So I'm going to propose that anytime O wins, the score of the game is -1. Anytime X wins, the score of the game is a +1. And anytime nobody wins, the score is 0. So at this point, each of these boards have these values, -1, 0, and 1. So the goal, therefore, in this game of tic-tac-toe now is for X to maximize its score, because 1 is the biggest value available. And O's goal in life is to minimize its score. So that's how we take the fun out of the game. We turn it into math, where one player just wants to maximize, one player just wants to minimize their score. All right, so a quick sanity check here. Here's a board. It's not color-coded. What is the value of this board? 1, because X has, in fact, 1 straight there down the middle. So X is 1, 0, O is -1, otherwise a tie. So now let's see how we go about, with those principles in place, figuring out where we should play in tic-tac-toe. Now here's a fairly easy configuration. There's only 2 moves left. It's not hard to figure out how to win or tie this game, but let's use it for simplicity. It's O's turn, for instance. So where can O go? Well, that invites the question, well, what is the value of the board? Or how do we minimize the value of the board for O to win? Well, O can go in one of 2 places, top left or bottom middle. Which way should O go? Well, if O goes in top left, we should consider what's the value of this board. Is it minimal? Well, let's see. If O goes here, X is obviously going to go here. X is therefore going to win. So the value of this board is going to be a 1. Now, since there's only one way logically to get from this configuration to this one, we might as well call the value of this board by transitivity 1. And so O probably doesn't want to go there because that's a pretty maximal score, and O wants to minimize. Over here, though, if O goes bottom middle, well, then X is going to go top left. And now no one has 1. So the value of this board is thus 0. We might as well treat this as 0, because that's the only way to get there logically. So now O, more mathematically and logically, can decide, do I want an endpoint of 1 or an endpoint of 0? Well, 0 is probably the better option, because that's less than 1, and thus it's the minimal possibility. So O is going to go ahead in the bottom middle and at least force a tie. And so that's where you see evidence where if you humans are ever losing the game of tic-tac-toe, you have not followed their logic. But you could probably do it if there's just 2 moves left. But the catch is, let's go ahead and sort of rewind to 3 moves left. Here there are 3 blanks, and I've kind of zoomed out. The catch is that the decision tree gets a lot bigger the more and more moves that are left. It gets sort of bigger and bushier in that it's essentially doubling in size and width. And that's great if you have the luxury of writing it down on a piece of paper. But if you're doing this on your head while playing against a 5th grader, if I may, you're probably not drawing out all of the various boards and configurations trying to play it optimally. You're going with some instinct. And your instincts might not be aligned with an algorithm that is tried and true, minimax, that will ideally get you to win the game, but at least will get you to force a tie if you can't win. But tic-tac-toe is not that hard. I mean, how many different ways are there to play tic-tac-toe? We could write a computer program to pretty much play tic-tac-toe optimally. We could use code like this. If the player is X, for each possible move, calculate the score for the board at that point in time, and then choose the move with the highest score. So you just try all possibilities mathematically, and then you make the decision. Most of us in our heads are not doing that, but we could. Else, if the player is O, essentially do the same thing, but choose the minimal possible score. So that's the code for implementing tic-tac-toe. How many ways are there to play tic-tac-toe, though? Well, 255,168, which means if we were to draw that tree, it would be pretty darn big, and it would take you quite a bit of time to sort of think through all those possibilities. So in your defense, you're maybe not that bad at tic-tac-toe. It's just harder than you thought as a game. But what about games with which we might, as adults, be more familiar? Well, what about the game of chess, which is often used as a measure of like how smart a computer is, whether it's Watson back in the day playing against it or something else? Well, if we consider even just the first 4 moves of tic-tac-toe, whereby I mean black goes and white goes, and then they each go 3 more times, so 4 pairwise moves. How many different ways are there to play chess? Well, it turns out 85 billion just to get the game started. And that's a lot of decisions to consider and then make. How about the game of Go, if familiar? Consider the first 4 moves, 266 quintillion possibilities. And this is where we sort of, as humans, and even with our modern PCs and Macs and phones, kind of have to throw up our hands, because I don't have this many bytes of memory in my computer. I don't have this many hours in my life left to actually crunch all of those numbers and figure out the solution. And so where AI comes in is where it's no longer as simple as just writing if, else's, and loops, and no longer as simple as just trying all possibilities. You instead need to write code that doesn't solve the problem directly, but in some sense indirectly. You write code so that the computer figures out how to win, perhaps by showing it configurations of the board that are a good place to be in, that is promising, and maybe showing it boards that it doesn't want to find itself in the configuration of, because that's going to lead it to lose. In other words, you train it, but not necessarily as exhaustive. And this is what we mean nowadays by machine learning, writing code via which machines learn how to solve problems, generally by being trained on massive amounts of data, and then in new problems looking for patterns via which they can apply those past training data to the problem at hand. And reinforcement learning is one way to think about this, in fact. And in fact, we as humans use reinforcement learning, which is a type of machine learning, sort of all of the time. In fact, a fun demonstration to watch here involves these here pancakes. So in fact, let me go ahead and pull up a short recording here of an actual researcher in a lab who's trying to teach a robot how to flip pancakes. So we'll see here in this video that there's a robot that has an arm that can go up, down, left, right. This, of course, is the human, the researcher. And he's just going to show the robot one or more times like how to flip a pancake. And crosses his fingers. And OK, seems to have done it well. Does it again. Not quite the same, but pretty good. And now he's going to let the robot just try to figure out how to flip that pancake after having just trained it a few different times. The first few times, odds are, the robot's not going to do super well because it really doesn't understand what the human just did or what the whole purpose of. But, and here's the key detail with reinforcement learning, behind the scenes, the human is probably rewarding the robot when it does a good job. Like better and better it flips, the more it gets rewarded, as by like hitting a key and giving it a point, for instance, or giving it the digital equivalent of a cookie. Or conversely, every time the robot screws up and drops the pancake on the floor, sort of a proverbial slap on the wrist, a punishment so that it does less of that behavior the next time. And any of you who are parents, which by definition today many of you are, odds are, whether it's not this or maybe just verbal approval or reprimands, have you probably trained children at some point to do more of one thing and less of another. And what you're seeing in the backdrop there is now just a quantization of the movements, x, y, and z coordinates, so that it can do more of the x's and the y's and the z that led it to some kind of reward. And now after you're up to some 50 trials, the robot seems to be getting better and better, such that, like a good human, we'll see if I can do this without embarrassing myself, can flip the thing. That's pretty good. I've been doing this a long time. OK. So we've seen then how you might reinforce learning through that kind of domain. Let's take an example that's familiar to those of you who are gamers. Anytime you've played a game where there's some kind of map or a world that you need to explore, up, down, left, right, maybe you're trying to get to the exit. So here, simplistically, is the player at the yellow dot. Here, for instance, in green is the exit of the map, and you want to get to that point. And maybe somewhere else in this world, there's a lot of like lava pits. And you don't want to fall into the lava pit because you lose a life or you lose a point, or there's some penalty or punishment associated with that. Well, we, with this bird's eye view, can obviously see how to get to the green dot. But if you're playing a game like Zelda or something like that, all you can do is move up, down, left, right, and sort of hope for the best. So let's do just that. Suppose the yellow dot just randomly chooses a direction and goes to the right. Well, now we can sort of take away a life, take away a point, or effectively punish it so that it knows don't do that. And so long as the player has a bit of memory, either the human player or the code that's implementing this, just with a dark red line, that means don't do that again, because that didn't lead to a good outcome. So maybe the next time the yellow dot goes this way, and then, it didn't realize that that's actually the same lava pit, but that's fine. Use a little bit more memory and remind me, don't do that because I just lost a second life in this story. And maybe it goes this way next time. Now I need to remember, don't do that. But effectively, I'm either being punished for doing the wrong thing, or, as we'll soon see, being rewarded for doing more of the successful thing. And just by chance, maybe, I finally make my way to the exit in this way. And so I can be rewarded for that. Now I got 100 points, or whatever it is, the high score. So now, as per these green lines, I can just follow that path again and again, and I can always win this game. Kind of like me nowadays, like 30 years later, playing Super Mario Brothers, because I can get through all the warp levels, because I know where everything is, because for some reason that's still stored in my brain. Is this the best way to play? Am I as good at Super Mario Brothers as I might think? What's bad about this solution? Yeah? Exactly. Yeah, I've moved many more times than I need to. And just for fun today, what grade are you in? Seventh grade. Wonderful. So now 7th grade observation is like exactly that we could have taken a shorter path, which is essentially that way, albeit making some straight moves. And so we're never going to find that shorter path. We're never going to get the highest score possible if I just keep naively following my well-trodden path. And so how do we break out of that mold? And you can see this even in the real world. Another sort of personal example is I'm the type of person, for some reason, where if I go to a restaurant for the first time, I choose a dish off the menu and I really like it, I will never again order anything else off that menu other than that dish because I know it is good. But there could be something even better on the menu, but I'm never going to explore that because I'm sort of fixed in my ways, as some of you from the smiles might be too. But what if we took advantage of exploring just a little bit? And there's this principle of exploring versus exploiting when it comes to using artificial intelligence to solve problems. Up until now, I've just been exploiting knowledge I already have. Don't go through the red walls, do go through the green walls. Exploit, 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 and I will get to a final solution. But what if I just sprinkle in a little bit of randomness along the way, and maybe 10% of the time, as represented by this epsilon variable, I, as the computer in the story, generate a random number between 0 and 1. And if it's less than that percent, which is going to happen 10% of the time, I'm going to make a random move instead of one that I know will get me closer to the exit. Otherwise, I'll indeed make the move with the highest value. Now, this isn't going to necessarily win me the game that first time. But if I play it enough and enough and enough and insert some of this randomness, I might very well find a better solution and therefore be a better player, a better winner overall. If I just 10% of the time ordered something else off the menu, I might find that there's an amazing dish out there that otherwise I wouldn't have discovered. And so indeed, using that approach, can we finally find a more optimal path through the maze, as was shorter there, presumably therefore maximizing our score and doing even better than we might have by just exploiting the same knowledge. So you can see this even in the game of Breakout, especially if you write a solution in code to play this game for you. Let me go ahead and pull up another video recording of an AI playing Breakout. And what this AI is doing is essentially figuring out, maybe more intelligently than you or I could, how to play this game optimally. And what we'll see here is that just like the pancake flipping robot, there's some notion of scoring and rewards and penalties here. So like right now, the paddle's just doing random stuff. It doesn't really know how to play the game yet. But it realizes after 200 episodes that, oh, my score goes up if I hit the ball, and it goes down equivalently if I miss it. And it's still a little twitchy. It doesn't quite understand what it's supposed to do and why. But if you do it again and again and again, and it's rewarded and or punished enough, you'll see that it starts to get pretty good and closer to what a good human might do. But here's where the algorithm gets a little creepy. If you let it play long enough, or if you and I, the humans, play long enough, you might find a certain trick to the game. I dare say the AI becomes a bit scarily sentient in that, turns out, if you're smart enough to break through that top row, you can let the game just play itself for you and maximize your score without even touching the ball. Something that I do find a little creepy, that it just figured out how to do that without being told, but it's just a logical continuation of rewarding it for good behavior and punishing it for bad behavior. So that next time you have an occasion to play Breakout, consider that kind of strategy as opposed to doing more of the work yourself. Let the computer do it for you instead. Well, what else is there to consider in this world of AI in the context of machine learning? Well, there's specifically a category of learning that's supervised. And we've been using this for years. And in fact, our first example of spam early on was certainly supervised. Why? Because it was you and I who was like putting the email into the spam folder. And to this day, maybe once a day, I hit the keyboard shortcut in Gmail to say, this is spam. You should have caught this. And that is training Google's algorithm further, assuming it's not just little old me, but maybe thousands of people tagging that same kind of email as spam. That's supervised learning, and that there's a human in the loop doing at least something. So spam detection might be one of those. But the catch is that labeling data in that way manually just doesn't scale very well. That would be akin to having someone at Google or Microsoft labeling every email, or someone at Netflix doing the same for all of the videos out there. It's expensive in terms of human power, and there's certainly problems out there with so much data. It's just not realistic for humans to label millions of pieces of data, billions of pieces of data. We've got to move to an unsupervised model. And so this is where the world starts to consider deep learning, solving problems using code whereby you don't even have humans in the loop in quite the same way. And neural networks, inspired by the world of biology, are sort of the inspiration for what is the state of the art, even underlying today's rubber duck, and more generally, these things called large language models like ChatGPT and the like. So here, pictured somewhat abstractly, is a neuron, and it's something in the human body that transmits a signal, say, from left to right electrically. And if you have multiple neurons, you can intercommunicate among them so that if I think a thought, then I know how to raise my hand because some kind of message electrically has gone from my head to this extremity here. So that's, in essence, what I remember from 9th grade biology. But as a computer scientist, we sort of abstract all of this away. So instead of calling these two neurons, drawing them as neurons, let's just start drawing neurons as these little circles. And if they have connective tissue between them of sorts, we'll just draw a straight line, an edge between them. So this is what a computer scientist would call a graph. If you have two such neurons over here leading to one neuron here, you can think of this as being like maybe two inputs to a problem, and now one output there too. We can represent the notion of problem solving, which is what CS50 and intro courses more generally are all about. So let's solve a problem with a neural network without necessarily training it in advance, just letting it figure out how to answer this question. Here's a very simple two-dimensional world, XY grid, and here are two dots. And the dots in this world are either blue or they are red, but I have no idea yet what makes a dot blue or red. However, if you train me on those two dots, I bet I could come up with predictions, especially if you let me label this world in terms of x coordinates on the horizontal, y coordinates on the vertical. And then you know what? We can think of this neural network very simply as representing the x coordinate here, the y coordinate here, and the answer I want to get is quote unquote red or blue, or 0 or 1, or true or false, however you want to think of the representation. So how do I get from a specific xy coordinate to a prediction of color if I only know the coordinates? Well, from the get-go, maybe the best I can do is just divide the world into blue dots on the left and red dots on the right, a best fit line, if you will, based on very minimal data. Of course, if you give me a third dot, it's going to be pretty easy to realize that I was a little too hasty. That line is not vertical, so maybe we pivot the line this way, and now I'm back in business. Now I can predict with higher probability, based on xy, what color the next dot will be. You give me enough of these dots, I can come up with a pretty good best fit line. It's not perfect, but here's a hint at why AI is not perfect. But 99% of the time, maybe I'll be able to predict correctly. And I can do even better if you let me squiggle the line a little bit and maybe make it more than just a simple slope. So what is it we're really doing with implementing this neural network, albeit simplistically with just 3 neurons? Well, essentially, we're trying to come up with 3 values, 3 parameters, an A, a B, and a C. And what do those represent? Well, really just a solution to this formula. That there line we drew can be represented, if you think back to like high school math, with a formula along these lines, whereby it's A times X plus B times Y plus some constant C. And we can just arbitrarily conclude that if that value mathematically gives me a number greater than 0, predict it's going to be blue. Otherwise, predict it's going to be red. We can sort of map our mathematics, just like with tic-tac-toe, to the actual problem we care about by defining the world in this way. And so if you give me enough data points and enough data points, I can come up with answers for that A, that B, that C, the so-called parameters in neural networks. Now, in reality, neural networks are not composed of like 3 neurons and a couple of edges. They look a little something more like this. And in practice, they've got billions of these things here on the screen, in which case, pretty much every one of these edges represents some mathematical value that was contrived based on lots and lots of training data. And whereas I, the computer scientist, might know what these neurons over here represent, because those are my inputs, 3 in this case, and I, the computer scientist, know what this one represents at the end, if you sort of took the hood off of this thing and looked inside the neural network, even though there'd be millions, billions of numbers going on there, I can't tell you what this neuron represents or why this edge has this weight. It's because of the massive amount of training data that's just how the math works out. And if you feed me more data, I might change some of those parameters more. So the graph ultimately might look quite different, but my inputs and my outputs are going to be what I use to solve that there problem. So if you want to predict like rainfall from humidity or pressure, you can have 2 inputs giving that one output. An advertising dollar spent in a given month, that might predict sales by just having trained, again, on such volumes of data. And when we get now full circle to something like CS50's rubber duck and large language models like Claude and Gemini and ChatGPT, What's really happening, and this is all hot off the press in recent years, screenshotted here are some of the recent research papers that have driven a lot of this advancement in recent years. You have, from OpenAI, say, a generative pre-trained transformer, which is a lot to say, but there's the GPT in ChatGPT. And essentially, this is a neural network that's been trained on large volumes of textual information that gives us the interactive chat feature that we have in the class, and we all have more generally in ChatGPT itself. So an example of what is actually happening underneath the hood of these GPTs. Well, here's a paragraph that up until recent years was kind of a hard paragraph to end with the ... Massachusetts is a state in the New England region of the northeastern United States. It borders on the Atlantic Ocean to the east. The state's capital is ... Now, most anyone living in Massachusetts probably knows that answer. But if this AI has just been trained on lots and lots of data, there's probably a lot of people who say Massachusetts in part of a sentence and then the answer, which I won't say yet, is in the other part of the sentence. But in this example, given that the question we're asking is sort of so far from some of the useful keywords, up until recently, this was a hard problem to solve because there was so much distance. Moreover, there's these nouns that are being used to substitute for the proper noun. Like we suddenly start calling it a state. We call it a state down here. And it wasn't necessarily obvious to AIs that we're talking about the same thing, as if it were just city, comma, state, where you'd have much more proximity. So in a nutshell, what we now do, especially to solve problems like these, is we first break down a sentence or the training data or input alike into like an array or a list of the words themselves. We come up with a representation of each of these words. For instance, the word Massachusetts, if you encode it in a certain way, is going to be represented with an array or vector of numbers, floating point values, so many so that the word Massachusetts in one model would use these 1,536 floating point numbers to represent Massachusetts, essentially in an n-dimensional space. So not just an xy plane, but somewhere sort of virtually out there. And then, and this has been the key to these GPTs, an attention is calculated based on all of that data, whereby in this picture, the thicker lines imply more of a relationship between those two words. So Massachusetts and state is inferred as having a thicker line, a higher attention from one word to the other, whereas our a's and our is's and our thes have thinner lines because they're just not as much signal to the AI as to what the answer to this question is. Meanwhile, when you then feed that sentence, like the state's capital is, one word per neuron here, the goal is to get the answer to that question. And even here, this is way smaller of a representation than the actual neural network would be. But in effect, all these LLMs, large language models, are just statistical models. Like, what is the highest probability word that it should spit out at the end of this paragraph based on all of the Reddit posts and Google search results and encyclopedias and Wikipedias that it's found and trained on online? Well, the answer hopefully will be Boston. But of course, 1% of the time, maybe less than that, the answer might not be correct. And even CS50's own duck is fallible, even though we've written lots of code to try to put downward pressure on those mistakes. And those mistakes are what we'll call, lastly, hallucinations, where the AI just makes something up, perhaps because some crazy human on the internet made something up and it was interpreted as authoritative, or just by bad luck, because of a bit of that exploration, 10% of the time, 1% of the time, the AI sort of veered this way in the large language model and the neural network and spit out an answer that just, in fact, is not correct. And so I thought I'd end for today on this final note, a poem with which many of us might have grown up from Shel Silverstein here, about the homework machine, which years ago somehow sort of predicted the state we would be in with these AI machines. He said, the homework machine, oh, the homework machine, most perfect contraption that's ever been seen. Just put in your homework, then drop in a dime, snap on the switch, and in 10 seconds time, your homework comes out, quick and clean as can be. Here it is, 9 plus 4, and the answer is 3. 3? Oh me, I guess it's not as perfect as I thought it would be. This then was CS50. See you next time.